Hey guys! In this video, we'll continue to develop a covariant form of Maxwell's equations, one that is fully compatible with general relativity. Before we continue though, I have to make a small correction. In the last video, I meant to restrict the discussion to arbitrary coordinate systems in flat spacetime, and I wanted to reserve the discussion of curved spacetimes for this video. But I got too carried away. A few times I used the phrase any spacetime, so my apologies. Anyway, in this video we arrive at the full Maxwell's equations for arbitrary spacetimes. In order to do that though, we need to go back to this set of equations, which we derived in this video. Notice that we can write this term like this, and this one like this. Bringing it to the other side, we can combine these terms to get this, and these terms to obtain this. Recall that we fixed the gauge by setting the divergence of A to 0, so as to cast the equation into a nicer form. However, let's not fix the gauge just yet. Now recall what we did in this video. By taking two derivatives of this tensor, we ended up with two possible terms. We discarded this one because in the limit of flat spacetime and Cartesian coordinates, it didn't match this equation. Only this term did. But that's because we had already fixed the gauge. If we leave the gauge alone, however, we must keep both terms. So the equation for the four-vector potential in the absence of any specific gauge is this. So why bother with all this? Why not just fix the gauge at the beginning and be done with it? Here's why. Notice that in flat spacetime, we can choose Cartesian coordinates in which the covariant derivatives turn into ordinary derivatives. The order of these two derivatives can then be flipped, leading to the divergence of A. However, in a curved spacetime, we can never find such a coordinate system. The best we can do is to find a coordinate system in which the Christoffel symbols are 0, but not their derivatives. This leads to an extra term, in addition to the ordinary second derivative. If you want a more detailed discussion of this, watch my alien-themed video. Okay, let's use the coordinate system where this is true to simplify this equation. We can rewrite this term by adding and subtracting this term. In these coordinates, this commutator reduces to this. Do you remember what this is? It's the Riemann tensor with these two indices summed over, which is just a Ricci tensor. So, this whole equation reduces to this. If we wanted to, we could fix the gauge now. Also, since the Einstein field equations in vacuum state that the Ricci tensor vanishes, for most problems this entire equation will look exactly like the one we derived in the previous video. Of course, if the electromagnetic field pervades the space, we no longer have vacuum. But in most problems, the geometry of spacetime will be governed by a large object, like the Earth or a star, so the contribution from the field itself will be negligible. Okay, before we move on, let us derive a couple of identities. First, let us show that the chain rule applies to a covariant derivative. I think we already used the chain rule in an earlier video, but I don't remember if we showed it to be true. In any case, repetition is the mother of knowledge, as they say where I grew up. So let's go through it. Let's take a product of two tensors, such that the result is a mixed tensor. The covariant derivative of this tensor is this. However, if chain rule applies here, then we can write this as the covariant derivative of the first tensor plus the covariant derivative of the second tensor, which leads to this expression. These terms combine to give this. These terms cancel out. What we're left with is this, which is exactly what we got before. So, the chain rule also applies to the covariant derivative. Another useful thing to know is the covariant derivative of the metric tensor. To figure out what this is, let's take an ordinary derivative of the metric expressed in terms of the bases. Applying the chain rule, and remembering what these are, we get the following, or this. But this is nothing but the covariant derivative of the metric. So, the covariant derivative of the metric is 0, always. You can show as a quick exercise that the same is true for the inverse metric. Okay, let's return to the original equation and recall the definition of the electromagnetic tensor in Cartesian coordinates and flat space-time. Two of the four Maxwell's equations follow from the divergence of F. Notice that in order to generalize this equation to arbitrary spacetimes, all we need to do is replace the ordinary derivative by the covariant derivatives and the flat spacetime metric with the general metric. We just showed that the chain rule applies and that the covariant derivative of a metric is 0. So we can slip these covariant derivatives past the metric, which leads us back to the original equation. So here's the first set of Maxwell's equations. Before we write down the second set, I want to show you guys something cool. Let's transform this tensor into its covariant form. Thanks again to the chain rule and the fact that the covariant derivative of the metric is 0, we can slip the metric past the covariant derivative and turn the contravariant vector A into a covariant one. Now let's expand this expression. But since gamma is symmetric in its lower indices, this term vanishes. So, the covariant electromagnetic tensor can be written in this simple form. It is now trivial to show that this relation is true. So, finally, we arrive at Maxwell's equations for arbitrary coordinates in arbitrary spacetime. Okay, that's all I have for this video. We'll continue to explore this subject in the next video. Cheers!